Okay, it's a pleasure to have Samory Kpotufe giving the second lecture in the summer school. Samory is an expert in machine learning and statistics. Graduated from University of California, San Diego, and has been a faculty at TTI Chicago and at Princeton before moving to Columbia, where he is currently an associate professor. And yeah, Samory is has done lots of exciting work, particularly at the intersection of, I guess, statistics, machine learning, some connection to metric geometry, and then Samory will tell us about the latest and greatest in machine learning.
Thanks, Madhur. I don't know if I'll be talking about the latest and greatest. What I will be talking about is very old, actually, but I hope that it would help stir interest in questions at the intersection of machine learning and statistics. So there is one thing, however, that I'd like quickly, if students here don't mind. Can you please come on video? I see that a lot of people just have their beautiful pictures up. Video is so much better because I get to see who I'm talking to and get a sense of whether what I'm saying is making sense at all, okay? All right, so thanks a lot, everyone, for coming online. Okay, so I'm going to be quite informal in the beginning, okay? And then we'll slowly get into more math, and especially tomorrow, we'll just get to really prove in detail some of the things we'll talk about today. But in any case, ask questions, okay? Stop me anytime, ask questions. It's always better in these short sort of courses that you understand a little bit than for me to talk so fast and say a lot of things that nobody follows. Okay, so I'd rather you stop me anytime. Okay, of course, if you're stopping too much, I'll stop you too. So here is the main thing I mean to talk about is universal learning possible. Right away, there are two things here. There's universal, and then there is learning, right? So before we can get into it, I have to first explain what do we mean at all by learning, and then get into what do we mean by universal, and then start answering the question, okay? So let me give you an outline of sort of what I'm thinking about doing today, actually over the next two lectures. So one, what do we mean by learning? And here I'll go over the various examples of learning problems. And then eventually a formal definition. Then here also, I'll talk about universality. So once we talk about universality, I'll talk about it informally. I'll introduce it informally to start, okay? And two, we get into formal definitions. And in particular, notions of rates, notions of consistency, notions such as so-called PAC learning. It stands for probably, approximately, correct learning. And then we ask the above questions again. 3, I'll mostly focus on the case of so-called regression, okay? And in the case of regression, so just to get a sense of, just to make it more precise what we mean by universal learning, I'll just focus on the case of regression, even though I'll define it very generally to start. I'll focus on the case of regression. And in the case of regression, we'll discuss a very old learning procedure. K-nearest neighbor regression. And this very old learning procedure happens to be universal in various ways we might want to interpret the word universal, okay? And it will also turn out that universality is not possible in some cases, okay? Fairly generally, I'll start now. What is universal? We just want, in an informal way, we just want to ask the question, is there a universal intelligence? Can we make a machine capable of solving any learning problem out there? Okay, so that's sort of the high level question. So first, let's look at examples of learning problems. I would like these parts to be interactive. You guys help me come up with interesting questions that you guys know from the real world. And then we'll get into formalizing all of that. I hope that's clear. If you have any question, please unmute yourself and just ask the question, okay? All right. So one, we said, what do we mean by learning? And so examples of learning problems, usually learning is divided into two types of problem: unsupervised and supervised. Okay, so unsupervised learning, let's start with that. Unsupervised. I'll just give you examples. Here is an example, document clustering. Or document categorization. Okay, here quickly, who knows what document categorization is?
Will that be predicting the category of a given document?
Exactly. Okay, so document categorization, we represent the document somehow, and we want to predict the category of the document. Here, why it is called unsupervised, the type of samples we get, I mean, we all understand so far, I haven't talked about samples, but we all understand so far that when we talk about learning, the basic idea is that you have a bunch of observations, which we call samples. You have a bunch of observations. And then from those observations, you want to figure out something. You want to infer something about the population, okay? Or the distribution that generated the data. All right, so I'll have throughout this whole notion of there is some type of population. Here in the case of document categorization, it's all possible documents in the world, okay, in existence, all possible documents in existence, documents in the future, documents in the past. So that's my population, fine. And then I get a small sample from it. And from that sample alone, I want to return some function f hat that, given a document X, tells me the category. Y of that document. Does that make sense? Okay, so samples documents represented somehow. Output of the learner, a function, a mapping, f hat, which given document X returns a category. Here, the category could be the document is about sports, the document is about music, the document is about politics, etc. Okay, makes sense to everyone? Now, the key point here, why we call it unsupervised, is that the type of samples we have is just examples of documents, but without what we call supervision, which is without the labels of the documents. We are not given, for instance, that this document, this particular document is about music, this document is about politics. We are not told that. We are just given the document, and we want the learner to figure out somehow that in this set, in this corpus of documents, in this sample, there are all these groupings. Does that make sense? Any question here?
Yeah.
All right. So we call that unsupervised. And let me give you, using again document categorization, let's talk about the supervised case, B, supervised. The only difference here, let's say it's again about document, and now I'm given xi, yi, let's say n samples, I1 through n, where xi is a document, yi is the category of the document. Okay, we call this supervised because I'm telling the learner a lot more. I'm not just giving the learner just the document and asking the learner to figure out that there are groups within the document. I'm giving it the actual labels. Makes sense to everybody? So we call that supervised learning. In this particular case, this is called classification. Again, the output is a function f hat, which is the category of the document, of a document. Okay, so what do we want? We want it to be that upon observing just n samples, let's say little n is 1,000 samples. Okay, the learner f hat is able to tell me the category of a future document X that it has not seen. Okay. And that's the key point. I want it to be able to give me that mapping f hat that I can use on future documents. Make sense?
Do the supervised algorithms work better than the unsupervised versions?
Of course. That was actually my next question. Which problem do you think is harder? The unsupervised one is harder, right? Okay. And even as a human, it will be harder. If I just give you a bunch of documents, I've never told you about topics, and I'm telling you, these are grouped into 50 topics. Find the groupings. It's much harder, right? Does that make sense?
Yeah, thank you.
Mm-hmm. So hence, much of what I'll discuss today is the supervised case, okay? And it turns out that machine learning has been able to make a lot of advances in the supervised case. but not as much in the unsupervised case. Although there are tons of beautiful algorithms out there in the unsupervised case also. All right, if we have time, I can tell you a bit more about the unsupervised case, the type of things we might want to do. Okay. So let's look at other examples of classifications quickly. A common example that you guys have seen is, for instance, object recognition. And in object recognition, we have the same thing, xi, yi, I 1 through n. And now the xi's are pictures. The yi's are the object in the image. Okay, this is a place, for instance, where neural networks, you've all probably heard the word neural networks, do very well. Okay, in producing that function f hat. Fine with everyone? So here, I said I wanted this to be interactive. Which other example of classification problem could you come up with?
I feel like there could be some kind of traveling salesman-esque problem where there's like a map, or sorry, there's like a graph with weighted edges, and then you have to like take a couple paths through, and you want to find like the most efficient path through.
That could actually, I've never thought about that, but that could actually be viewed as a classification problem. But here, what you will have to do will be what? You'll have to give the learner a lot of such problems. Those will be X, a lot of graphs, and then the solution. That will be Y. Okay. And then you want the learner, just from the examples, to be able to solve future traveling salesman problems. Okay. So here, intuitively, I've given you a definition of learning already. What we mean by learning is really that after seeing a few examples, you can predict the category of a future example. Does that make sense? Then we can say that the machine is learning. Makes sense to everybody? Okay. Before we'll get into a formal the definition, but I just want at least the intuition to be there, to be clear. Another common example of classification problem would be speech recognition, right? Here, what is X?
Would you say?
Sorry?
The audio files and the corresponding like words.
X, audio file, a piece of speech. Y, the word, maybe that's being ordered. Okay. So makes sense to everybody? These problems are everywhere, right? Here, I'll start giving a sense of what we mean by universality. For each one of these problems, we tend to come up with a different learner that does well on that particular problem. Okay. And the high level idea of universality is, can we come up with a single learner that will do as well on object recognition or as on speech recognition, and completely agnostic to the actual problem and to the hardness of the problem? Does that make sense? A little bit, where we getting at? You can already imagine that some problems are much easier than the other problems. Recognizing the object in an image is a tough problem. It's a hard problem. Okay. But if the only thing I need to do is simple images of either a car or an orange, it becomes an easier problem. If that's the only two objects I need to be able to recognize. Does that make sense? A car versus an orange is an easier problem than all possible objects in the world. Okay. So there are various levels of hardness of these problems. And one of the questions of universality is there a learner that somehow independent of the level of hardness of the problem is able to find a good function f hat? Okay. So now in this, was there a question?
What is good here?
We'll define it in a second, okay? For now, good just means an f hat that doesn't make too many mistakes in categorizing the data, feature points, right? So if he sees a bike, it doesn't tell me it's a car, okay? All right, now the main, one main feature of this example so far is notice that the category Y is discrete. It can only take a finite set of values. Okay. Now we can jump into regression where Y can actually take various, a whole continuum of values. Okay. Before we jump into regression, however, I would like to bring in this notion of representation. Okay, how are we representing these xi and yi's? We have to represent it somehow to give it to the learner. Does that make sense? Okay, and so keep that in mind that we haven't talked about that yet. I'm right now generically telling you xi is a document. Fine. But I have to represent the document somehow. I'm not just feeding the document directly to the learner. I have to represent it somehow. Does that make sense? Okay. Xi is a picture. It's an image. I have to represent the image somehow. What are the key things I need to pull out of the image to give to the learner? So that question, we'll set it aside for now and jump into examples of regression. And then we'll get back to that question. Okay. So regression is the same setup as classification. But now, Y is continuous. Okay. Again, I observe many examples, xi, yi, 1 through n. And I want to output a function f hat of x, which is y. And y here is a continuous value in this case. So let's look at examples. Here is a simple example in agriculture. Okay. X represents the content of a soil content around the plant. Y is how fast the plant grows. Okay. X could be in climate, X could be the amount of CO2 in the air. Y could be, anybody help me here? The rise in temperature, for instance. Okay. The key point is that X is related to Y somehow, and we want to understand how X is related to Y. We believe Y is approximately some function f of X. We don't know. F, and we want to approximate it by the f hat that we infer from data. From the sample. Let me use a more, another example that is more modern. So brain-computer interface. So anybody's heard of BCI here, brain-computer interface? So have you might have seen on TV or in the news, imagine an amputee, okay? And the amputee has a robotic arm, fine? And the robotic arm is connected through sensors to the brain, fine? The brain sends signals, and the signals are really telling the arm to move up or down, open the hand, all sort of movements, okay? The way we come up with this new technology is essentially through regression. The X's here are brain signals. The Y is the intended movements. I'll just say intended action. But here the Y is viewed as continuous because the action move the arm right to left, let's say, move the arm right to left, by how much, okay? And how fast. Those are the Ys. And the way we train it is by collecting a lot of data from a human, brain signal data, and then we ask the human, what movement did you intend? By how fast? Does that make sense? And that's the Ys. And that's the data that we have. And from that data, we want to return an F hat, which again, on future signals will tell us the movement that was intended. I'll stop here for a second and see that all these examples are clear of intuitively the various aspects of learning. Any question? All right.
I have a question.
Go ahead, please. Can you speak a bit louder? I barely hear you.
And do you hear me now?
I do.
We define continuity by ourselves. I mean, that robot has some limits. It can't move very tiny. As I mean, it's discrete in somehow. And we define continuous ourselves or we really mean it can move in a very small details.
Oh, why am I viewing y as continuous in the case of BCI, in the case of brain-computer interface?
What? I couldn't hear.
Is that the question you're asking? Like,
Yes.
why am I viewing y as continuous?
Yes, I'm saying that it's not exactly continuous, and I'm asking if we define continuous by ourselves or we mean exactly, for example, like a line.
Oh, by continuous, I just mean that y is not a discrete. It's not a discrete set of values.
Okay.
Does that make sense?
Yeah, thank you.
Here, for the action, you don't have to view the action as left or right. You have to view the action as how far left, how far right, how fast. Does that make sense? So don't view y as a scalar. Y is not a scalar. Y is all these possible dimensions.
Thank you.
Okay. All right. Any other question?
So can you hear me?
Yep.
Yeah, so can we present y as a vector somehow was a
Yeah, here y in this last example, y can be viewed as a vector.
Okay, thank you.
Okay. All right. Okay, so we went through all these examples, and something that is common to the examples is some x and some y, right? And also this notion of, I'll put it in color, this notion of f, okay? Fine. And then the notion of f hat. All right. Okay. So let's start being a bit more formal. And we'll focus on the case of regression. Although I'll discuss classification in passing. There is x and there is y. The x, we're going to view the x as in a Euclidean space RD. Okay. In other words, x is really a vector x1, x2 through xd. And these coordinates, we call them features. Okay, we'll call those features. And y is the response / output. And generally, actually for simplicity, in this formalism, for simplicity, let y be in R. It's just a scalar. Okay. In the case where it's not a scalar, we can just stack up the problems. There are so many regression problems. Okay. So for simplicity, let's view it as a scalar. Let's think first about the notion of features. In the various examples so far, let's talk about document categorization. How can we represent a document? We can represent it, for instance, as a bag of words. We can just say, what I'm going to retain from a document is the words that appear in the document. Okay, so I can say that the first coordinate is the proportion of the word, football. X2, proportion of the word politics or government, etc. Okay. in the document. So those becomes the features of the document, the predictors that we pulled out of the document. Does that make sense? Okay. If I were to look at a different example, again, in classification, the example of object recognition. Then the excise through D could be the pixels of the image. Okay. For the agriculture, the excise could be, now help me out. What could it be? What could be the features here to represent the soil content?
Levels of nitrogen.
Exactly, the amount of particular molecules. Okay, X1 could be the amount of nitrogen, X2 could be the amount of water, etc. Does that make sense? Okay, in brain-computer interface, a signal, I can first do a fast Fourier transform of the signal and then take the Fourier component, and that's my X1 through XD. Make sense to everybody? Okay, so that's the notion of X. We will view, the key point here is that we're going to view X as in RD. Okay, as a vector, and we'll view Y as some output, a scalar output for simplicity. So the picture I'd like you to have in mind now is the following. And it's a picture from regression. We're going to assume, let's say this is RD, but this is R, D equal to 1, okay? We're going to assume that there is, in fact, some function f such that f of x is approximately y, but we don't know the function f. And all we know is, all we've observed is a few samples of x1 through xn through xn, okay? These are not the features of x. Now I'm viewing x as the complete vector, each one of these samples, okay? X1 through xn, and then the y values, the corresponding y values. This will be y1, this will be yn, okay? Is okay, it seems like my thing is not changing. Okay, I don't know what's just happened. Give me a second. Huh? If I change, okay, it's not changing. Let me stop sharing, reshare. Okay, so this will be y1, this will be yn. Okay, so these are what I've observed. And then from that observation, I'm supposed to return something, some f hat from just that observation that approximates f. Make sense to everybody? Okay. So we want to return an f hat that approximates f the f that is unknown, and we're viewing the f as the best possible predictor. F, best possible predictor of y. Okay, in classification, y will be the category. In regression, y will be the regression value. Okay. Fine with everybody, this picture? Any question here? And the hard part is f hat is learned from a finite sample of size n, which we've been calling xi, yi, 1 through n. So first, we need a notion of performance. How well does our learner perform? Okay. Before I even get there, one can think of all types of learners. All right. F hat here that I drew is one learner. I've only observed this. I haven't observed F. I've only observed this, right? So in fact, I could have come up with a different learner that just interpolates the data. Okay, that's one possible learner. I could have said a priori, I could have said instead that my learner, my F, I assume that my F is linear. Then if I had assumed that my F was linear before, I'd have never observed F, but I assumed that my F is linear, then the F hat that I would have returned would be a line. Okay. The key point I would like to make here is that my learner could have been anything. Make sense? Okay. And in particular, it could have followed any principle. A basic principle could be, I'm going to assume that the F that is unknown is actually a polynomial of degree 2. Okay. Then what I'll try to return is the best polynomial of degree 2 that sort of fits the data. If I assume it's a line, I'll try to return the best line that fits the data, etc. And this point is very important. Because I do not know F, any learner that I come up with has to somehow make an assumption about what F I may expect. Is that clear to everyone? Then from there, we can ask the question, how do we measure the performance of F? When somebody asked earlier, when do we say that F is good, that the F hat that I return is good? Okay, so I can say F hat is good if it's close to F under some notion of distance. Okay, so I want, in other words, we want distance F hat to F to be small, to be below some epsilon. Okay, we want that distance to be small, and we can come up with all sorts of notions of distance. So here is a notion of distance. Example, L2, it's called L2 distance. I can say, for instance, that the integral f hat of x minus f of x squared dx is small. And that becomes my notion of distance.
Can I ask,
Go ahead.
in order to be able to measure this distance, we would need to know F as well.
Exactly. However, that's the beauty of math. We'll be able to say something about these distances in general,
okay,
without knowing F.
But I mean, okay, in practice though, we wouldn't know for certain that there isn't some point where F hat acts like really poorly on.
Exactly, we would not know in practice. And so what we do then in machine learning, and that's exactly where these questions of universality comes in. Can I guarantee a priori that my particular algorithm, no matter what the function f is going to give me a small distance? Does that make sense? So you're leading to the main question that we're going to start trying to ask, okay?
Do
Go
we
ahead.
only measure distance at like the target points that came in our input set? So like,
No, that's a very good question too. Let's go back here, right? I keep saying future. It means X was not in our sample. Okay, and that's the challenge. And that, suppose that we can only return a good value of f for points in our samples. It's not quite learning yet. Make sense?
yeah. So like, I guess when we're doing this distance comparison, we do that distance comparison on future like points as well.
That's what I mean here by dx. So for instance, suppose that we are on the real line, x is in R, okay?
Mm-hmm.
This is f unknown. This is my f hat that I return.
Right.
I'm asking that on average, over the entire real line, these two things are close to each other.
Okay.
Does that make sense?
Yeah. Will we get to
We'll get to how we can assess these things.
Okay.
Okay.
Awesome. Thank you.
And how we can assess it is going to be about what we call a universe. It's going to be what I'm calling a universe. What assumption am I allowing myself to make about f? Okay. If I make absolutely no assumption about f, then the problem gets hard. The problem gets nearly impossible. Does that make sense? But I would like to be able to say that in this very large class of possible f's, and that will be the universe, in this very large class of possible f's, my algorithm f hat is going to always minimize this. Okay, and that's a guarantee I give a priori about the algorithm, and now I can release the algorithm to the real world. Does that make sense to everybody? So now I'm going to bring in another notion, the notion of a distribution. And that's going to become important in much of what we discuss. Give me 1 second. So, by the way, in practice, I can try to measure a different notion of performance. Just to answer your question in a more practical way, okay? I can try to measure a different notion of performance. So this is the notion of performance. I can ask the question, what's the error of f hat on future data? And try to estimate that error on future data. Hence, if the error of f hat on future data that I estimate is small, intuitively, that should mean that f hat is close to f which is the one that has the smallest possible error on feature data. Does that make sense? So how do I measure error of f hat on feature data? I can set some data aside. Okay. I have my training data. This is usually called my training data, the sample from which I learn f hat. And then I set a different set of samples aside. And then I test on that sample whether f hat approximately recovers the y's that he hasn't seen. Okay. So in practice, and that's called cross-validation. I'm validating my f hat on a different sample. And that's usually what we do in practice to get some level of confidence that it's going to do well. Okay. And then we add math to be able to say that it's going, in fact, to do well on a very large set of problems. Because what is the issue with the cross-validation that I just gave you? What is the distinction? Okay, let me just say it. The issue is that the only thing my cross-validation is telling me is whether my f hat is doing well on my particular problem. Does that make sense to everyone? Because I only have data from my particular problem. If I want to be able to say it's going to do well in general, then that my procedure, my approach of learning is going to do well in general, then I need to use math, because I do not know, I will not be able to test all possible data sets out there, all possible problems out there.
I have a quick question.
Mm-hmm.
So would you say that the only way to truly know the true performance of an algorithm is by actually having all of the data available for the problem, I guess, in existence?
No, I don't mean all the data available to the problem. I would try to use some data to have a sense of, is it doing well on future data, right? Let's suppose that I set aside 1,000 samples. It gives me some sense that it's doing well on future data. If I only set aside 10 samples, I will not know. I would not be as confident. Does that make sense? But now, the point I'm making, the nuance I'm making is here. We went through all sort of examples, right? So brain-computer interface, agriculture. If I'm dealing with agriculture and my procedure, my learner does well on my data from agriculture, it doesn't tell me it's going to do well on my data from brain-computer interface. Does that make sense? Okay. Because the F, the unknown F in the agriculture case might be a completely different function than the unknown F in the brain-computer interface case. And so hence, we asking this question of universality. Is there one algorithm that if I give it data from here, or I give it data from here, it's going to do well in both cases? Does that make sense? Okay. So here, let's continue on this notion of distance here. We may instead, so suppose that in fact, X's are sampled, the Xi's are sampled IID from a distribution mu X, from a probability distribution. Okay? You following me? Then all I mean by that is rather than measuring how far f hat is from f on the entire real line, I might just want to measure it with respect to the most likely values of Xi's that I might see in the future. okay? In which case, I should take into account the probability distribution of my xi's, okay? So then another measure is L2 mu x measure, where instead I have f hat of x minus f of x squared d mu of x, where I integrate with respect to that measure, okay? Does that make sense? So what is this? For those of you who have seen, and I hope most of you guys have had a bit of probability, this is just the expectation of f hat of x minus f of x squared. Okay? Fine. And that would be a measure of future performance. And if this thing is small, then I say my f hat, my learner is good. At least it's approximately good. Does that make sense? Okay. I could even, let me give you other examples quickly. I could even define the distance between f hat and f as something different. I could say that I want f hat to do as well as possible on any data point I might see. Okay. So that will mean I'm looking at the sup over all possible x of f hat of x minus f of x. That will be a measure of performance. Okay. There are tons of measures of performance out there. We just pick one. Okay. Sometimes the actual problem dictates the measure of performance that we may use.
Sorry, I had a question about that.
Go ahead.
So does that mean that for any possible epsilon arbitrarily small that you can like that there is no like you cannot necessarily construct a f hat of x?
So we'll get to that in a second. Okay. So but the key point I'm making so far is that there are different ways of measuring how close f hat is to f. We just pick one. Fine. Everybody agrees with that? Okay. Now, we can come up now using that to a formal definition of learning. Probably approximately correct learning. Okay. Fine. It's just going to say that for any approximation level epsilon, any confidence delta, okay, the probability that the distance between f hat and f is less than epsilon is greater than 1 minus delta for n, for the sample size sufficiently large. Okay. The probably is here. The approximately correct is here. Okay. We say f hat is approximately correct if the distance between f hat and f is below epsilon. We say that it's probably approximately correct if it's probably approximately correct. Okay. The probability is large. This way of writing just means that the probability is large. You view epsilon and you view delta as very small things. What is the probability on? A probability is always over some randomness. What is the probability on? What is the randomness here?
Will it be f hat?
F hat exactly is random, but where is f hat taking its randomness from?
From the algorithm that's supposed to approximate it?
No. F is what we're trying to approximate. Okay.
From the real world data.
From the data. F hat was learned from the data. The data is random. Okay. So the probability here is over the randomness in the sample. In the sample used to learn F hat, to infer or to return F hat. Okay. Does that make sense to everybody?
I have a quick question.
Mm-hmm.
So will the distribution affect this in any way? I mean, with respect to the data.
Yeah. The distribution of, so it's what we mean by this is the randomness. We mean that XIYI was IID. We're going to assume that it's independently and identically distributed according to some distribution PXY. Okay. I'm going to call it mu XY so that I've used mu X here, so I'll keep using that, mu XY. We assume that this is a random sample from some distribution. Okay, to link back to what I said earlier, let me see where I drew it. I said earlier, we're going to view things as being drawn from a population. And then I have my sample. Now, more formally, saying that it's drawn from a population is just saying that it's IID from some distribution. Okay. All right. With everybody? Okay. So now it's IID from some distribution. Now, the distribution may be easy or maybe a hard distribution. Okay. And that would affect the performance of my FHAT, of my algorithm. We haven't discussed an actual algorithm yet, but hopefully by in the next 20 minutes or so, I'll discuss some algorithm. Okay. Fine. With everyone? So this is the key thing that we want. It's called probably approximately correct learning. And this is how machine learning people have defined learning a long time ago. All right. It so happens that when machine learning people were defining learning this way, they didn't realize that statisticians had already defined it that way 100 years prior. Jamboard crashed on me. Give me a second. All right. Okay. So, so they define it this way. And what I was saying is that it actually was defined already by statisticians. And the one piece missing here that I called in what I call probably approximately correct is that F hat should be an efficient, a computationally efficient procedure. Okay. We want it to be, for instance, polynomial time in the parameters here, the dimension of the data, the sample size, and all that. Okay, fine. So that's the only distinction between the definition that machine learnists gave and an earlier definition by statisticians, and where they just call it consistency. Okay, so we say F hat is consistent for F if for all epsilon greater than 0, probability that the distance F hat F less than epsilon, that probability as n goes to infinity, that probability goes to 1. Okay. Make sense to everybody? All right. Are there questions? I'm seeing it's hard to read faces right now.
Just to make sure, so this is saying that as we, I guess, approach infinity with n being the number of samples coming into
And
the
being the number of
algorithm?
samples, exactly. So we're just going to say we want our algorithm to at least satisfy this, that we will say that our algorithm is learning if it at least satisfies this, as it's given enough samples. And don't forget, here I already have for sufficiently large sample size. Okay. If I just gave the algorithm 2 observations, I should not expect it to learn much from 2 observations. Does that make sense? But all it's saying is that if you give me an approximation level, epsilon, call it 0.001, 0.000001, whatever it is, there is a sample size large enough for the probability to be large. Okay.
And just really quick, and this will be for perfect data, right? That has no noise.
Sorry?
So will this also apply for
We
data
just
that has no
want we just want the data to be representative. That's what we mean by IID. It's independent and identically distributed from a particular distribution. Okay. Make sense to everybody? All right. So let me now define universality. Okay. So universality so we may now consider a large, accent on large, a large class of functions, big F, our universe, a set of all possible problems, okay, and ask whether F hat is consistent for any F in big F. Can he learn any function in our large class? Does that make sense? So in this definition here, all I'm saying is the same F hat, I don't mean the same function, but the same algorithm. Here, I'm viewing F hat both as a function and as an algorithm. Okay. There is the algorithm that returns the function, and then there is the function. I'm conflating the two. F hat, I'll just use F hat for the algorithm that returns F hat. Make sense to everybody? Okay. And so I'm saying, can that algorithm, no matter how large my class F is, return an F hat that approximates F, no matter what F is in that large class? Okay. I can say that my big class F is all polynomials of degree of degree 10. That's a class. Okay. It's not that large, in fact, when you think about it, because I can go even larger. F is all continuous functions. Okay. And now, if I have an algorithm that for all continuous functions does not know the function a priori, always returns something that actually learns that function, then I can say in some sense that that algorithm is universal. Does that make sense? Again, back to the drawing, the function f could have been this. That's a continuous function. It could be this. It could be this. And what we're saying is that an algorithm f hat is universal if no matter f in f, it can learn it given enough samples. Okay. Let's quickly talk about an algorithm that is not universal. Let's give a simple one. Here is a dumb algorithm. It looks at the data and it always returns a constant function. It looks at the data and it returns y bar. And y bar is equal to f hat of x for all x. It's a constant function. Okay? The average of all the y values it observed. Fine. That function, that f hat always returns something like this or like this, depending on the y values that it observed. Okay? It's clear that that's not a consistent algorithm with respect to the class of all continuous functions. Does that make sense? Fine. However, that algorithm is consistent with respect to one function.
If we define the distance as maximum average of f minus average of f hat, if that was our distance function, then this approach would
yeah. So it depends on the distance function, but I'm saying let's think of a reasonable distance function. Okay. Let's think of a reasonable distance function like the maximum deviation between any 2 points, f of x and f of and f hat of x, or the average or this L2 distance, the expected deviation. Okay. Then clearly such a constant function will not be consistent. All right. So let's think of another algorithm that will not be consistent. It could be a simple algorithm. It's an algorithm that always returns a line. Okay. It will be consistent with respect to the class of all lines, but it would not be consistent with respect to all continuous functions. Make sense to everybody?
I have a brief question, if it's okay.
Mm-hmm.
In the definition of universality, you also say that we want to be consistent for any f, but also for any possible choice of probability distribution, right?
Oh,
not just for one.
So yeah, that's a very good question. You can define consistency also by restricting the class of probability distributions. And then that becomes your universe. The key point is, what is your universe? Your universe might just be a fixed one class of probability distributions on X, for instance. And I say that the best function f comes from a larger class f. Make sense? And then that's my universe. However, technically, the question you're asking is a very nice question, because technically, I have to define my universe in terms of not only big F, but the set of probability distributions I'm allowing. Okay.
Thanks.
For the particular algorithm we will discuss next, it doesn't matter the class of probability distributions. Fine. As long as we're in a Euclidean space.
That's okay.
Okay, with everybody? All right, so we have 10 minutes left. I'm going to now just give you, so this is essentially part 3. before I even go further, I'll just tell you, one can actually go to an even tougher notion of universality. Rather than just talking about consistency, okay, I can talk about rates of convergence. Note, we can ask for stronger guarantees. In terms of rates of convergence. Okay, so here, rather than saying for all epsilon, I can say that for some sequence epsilon n, we have that probability that f hat, that the distance between f hat and f less than epsilon n is greater than 1 minus epsilon n. Okay, so epsilon n might be 1 over n or 1 over square root n or anything. Okay, and epsilon n is then called a rate of convergence. Okay.
A rate of convergence.
Because I'm asking, under my notion of distance, how fast is f hat going to f? Rather than just saying that f hat is eventually getting to f if the sample size is large enough. I'm asking, how fast in terms of the sample size is it arriving at f? Okay. Does that make sense to everybody? And then assessing this gets a bit even a bit tougher. All right. Because it could be that f hat gets to f, but it gets to f very slow. All right. So in addition, what people in machine learning theory do is they try to understand the rate of convergence. How fast is it getting to f? And then you can define universality in terms of the rate of convergence. You can say, for every given problem, we sort of have a sense of what is the best possible rate of convergence? What is the best possible algorithm for that problem? And then in that case, I'll say that an algorithm is universal if it is capable of achieving the same rate of convergence as the best possible algorithm for any given problem in a particular family of problems. Okay, and that's a tougher type of universality. And that type of universality, one can show that no such algorithm exists in general. Okay. So an algorithm that is as good as the best algorithm for every problem doesn't exist. Somehow it means that we have to specialize our procedures for different types of problems. But we'll get back to that if we have time tomorrow. Let's just consider universality with respect to get back to, if we have time. Universality, just with respect to consistency. A universality defined in terms of consistency. Okay? Fine with everyone? All right. So let me, before we go, let me define a quick procedure. 3 nearest neighbor procedures. And this is one of the oldest procedures out there, learners out there, and it is universal when it comes down to consistency. Okay, it's universal with respect to a lot of natural notions of distance. Okay, So here is the nearest neighbor procedure. I'm just going to illustrate it first in on the line. This is X, this is Y. And let's say that, again, this is the unknown function. Okay, this is F, it's unknown. And we've observed these data points for which we obtain these particular Y values. And now we consider a point little x, and we want a function f hat that gives us, that approximate the value of f at x. So quickly, the setup, just to remind you the setup of regression, we believe that y is approximately f of x. In fact, what we'll do is we'll make clear what we mean by approximately. We believe that y is equal to f of x plus some eta, where eta is a noise variable. Okay, fine. And in particular, the expectation of eta, the expected value of eta is 0. The mean of eta is 0. So all we mean is that the way nature generates the data is at the point x1, it first looks at f of x1 and then adds a bit of noise. Okay. It's a generic way to say that life is random. Okay. So now, here is one of the simplest algorithms that have always been there. Is I'm going to just say, I'm going to return this function f hat of x, which is defined as 1 over k, where k is a number that I specify. I'm going to call the function f hat k to make it clear that it depends on this value k that I have to specify. Some I in k and n of x, where I'm defining k and n of x as the k closest point to little x from the data x I 1 through n. Okay, suppose here that k is equal to 3, then the k closest points would be these ones. Okay, and I in k and n of x is viewed as the indices of the k closest points. And then I just average the y values of those k closest points. That's the nearest neighbor approach. Make sense to everybody? It's a very simple approach. It just says, let's imagine images. It just says, if I want to know the object in an image, let me take the closest images and say, and take, for instance, the majority object in the closest images and say that's that object. If the closest images to this particular image are images of dogs, I say this is a dog. Okay. It's intuitive, it's simple. So here it's saying, in regression, it's saying, let me take the closest x values. Let me look at, let me look at, here, let me erase one of this. Let me erase this one. So let me take the closest x values, and then let's look at the y values of them and take the average of those y values. And that becomes my estimate. The average is somewhere here. Okay, the average of these three values. And that's the k-nearest neighbor estimate.
Excuse
All
me,
right.
something. I was wondering if this approach, or how computationally efficient is this approach? Because I can imagine if the samples are really high dimensional, like an image, for example, how easy it is to find the 3 closest points.
So here, the closest, I'm imagining closest to be in Euclidean norm. Fine. How long does it take to compute the Euclidean norm to 1 data point? Order D, agree?
Yeah.
Okay. So I computed in order D. And in order D, I compute the Euclidean norm to 1 data point. I look at the n data point, so that's n times D. That allows me to find the first closest.
Okay.
Right?
Mm-hmm.
Then I remove, then I keep doing. So it's definitely polynomial time. Okay. However, now for the k-nearest neighbor approach, people have come up with all sort of data structures to do it even faster. Okay. I can do it faster. Why? Because I can, in fact, just do some type of, it's called branch and bound, some type of branch and bound method, where what I'll do is I can divide up my space already into large areas. And I can say, since the space is divided into large areas, I can ask which area is X in? If X is in that area, I'll only look at the points in that area. Right? And then I can build a hierarchy of such areas. I divide into big areas, I subdivide, and I keep repeating this, and you can do it in log time. Make sense?
Is that called k-dimensional tree?
There are various such trees. There is KD tree, there is random projection trees. So there are all sort of ways to divide up a high dimensional space. Okay.
Does that mean if you just move X a little bit, it doesn't change the value of F?
If the k closest neighbors, if I move X a little bit here, the k closest neighbors might remain the same.
Would that maybe ineffective, like since you change the X a little bit, but it doesn't reflect the change?
Why should that be ineffective?
Like suppose you have like not
the only reason I can change it and it doesn't change anything is that I have not observed F in those areas.
Right. And like suppose that the data is
so if I have not observed F in those areas, there is not much I can do.
Right.
Make sense?
Yeah, makes sense.
Okay. All right. So normally I should be finishing now, but let me use another couple minutes to bring up a quick question for you guys, okay? So let's think about this procedure. Should I choose K very large or should I choose K very small? Intuitively, K now is a parameter of the procedure, right? And the question is, should I choose that parameter very large or should I choose it very small? So let's think for now. Let's imagine I choose K very large, okay? Let's say that K is chosen to be essentially the sample size. K is close to N. What happens if K is chosen close to N?
Did it become a constant function?
Then it's not a good thing at all, right? Does that make sense? If K is chosen very large, it's not good. Agreed? Okay. What happens if K is chosen too small? Suppose K is chosen as 1.
There's a lot of bias.
Sorry?
There will be a lot of bias to the closest point.
Yeah. So it becomes a very, I'll use the term bias is a bit loaded because there is a natural definition of bias in stats. So I don't want to use the term bias, but it becomes very, if I choose K is equal to 1, then what is the closest point here? It's here, okay? That means that I'm returning this guy. So it's very much affected by the noise that was added by nature. I'm just feeding the noise. Does that make sense? If I chose k is equal to 1, let's say it's this guy, I just return f hat as this guy. So I really just return noise. Does that make sense? So too large of a k, too large of a k, f hat k, constant, bad. Okay, I should write bad with red color. Bad. Okay, it's not only constant, it uses all the data. Okay, it's the y bar of the data. Okay, fine. Too small. Too small of a choice, then I'm just feeding noise. Okay. Hence, what I need is to choose. What I need is to choose a value of k. Choose a middle value of k. And the question is, what do we mean by middle value of k? How can we choose it? But we just know that it cannot be too small, it cannot be too large. Okay. But this procedure is fairly general, it's fairly simple. And what we'll show tomorrow is that this simple procedure is universally consistent with respect to very large families of functions f. Okay. Very large families of function f, it will be universally consistent. And in what notion of distance? In various notions of distance. It can be shown to be consistent, universally consistent to large families, for instance, in L2 distance. Okay. And this is a very generous notion of distance. All right. And however, the proof that it is universally consistent is not the easiest proof. And so what I'll do is I'll just show you the main ingredients of the proof by looking at consistency in a consistency with respect to just a point. Okay, that if I fix a point x, no matter what f is, f hat would eventually get close to the value of f at x. Make sense? As long as f is continuous, for instance. So I'll stop here today. I won't really assign any homework yet. However, I've talked to the TAs, and the TAs would try to see today what to get deeper into. Tomorrow we'll use a lot of probability. And so if you don't remember your probability that well, try to revise it a little bit. Some of the exercises I've asked the TAs to do with you have to do with probability. Okay. So some basic tools in probability, expectation, how it works, playing around with expectation and things like that. So that's what we'll use to show that nearest neighbor regression is actually consistent in a very generic way. Okay. Any question?
Yes, I would have one if it's okay.
Yeah, go ahead, please.
So when you define parked learning, the definition I've seen is that you also allow for randomized algorithms fitting your function.
You could,
and then you just take the probability. Is there like any indication that
if you allow for randomized algorithm, then the probability is just not only over the sample. Where did I define it actually? Yeah, you're just allowing that the randomness in the probability part is also over the randomness in the algorithm.
Yes, and is there like any indication that randomized algorithms for these kind of function fits are strictly stronger than deterministic ones, or like is there any important negative results that holds for deterministic ones but not for randomized ones?
It's unclear. It's unclear because somehow, somehow in this line of work, people don't really try to take into account a randomized algorithm. The reason why is because the notion, because in practice, sort of what we want is an algorithm that does well deterministically. Does that make sense a little bit? So quite often we want the algorithm to return from the sample if it determines f hat, and that's usually how it's analyzed. And so that's a good question. I'll have to think about it, but I don't. It's not that studied in this line of work. Yeah, it is studied in some. How do you call that? The type of places where randomized algorithm appear, for instance, in so-called pack-Bayes theory. And in pack-Bayes theory, the question you're asking is negative. The hardness of learning is the same for randomized or non-randomized, right? So somehow they call them Gibbs classifiers, for instance, and the Gibbs classifier, rather than returning a single classifier, returns a distribution over classifiers and then randomly picks one to classify. And the best errors that are provable for it are no better than the best error provable for a deterministic one. That's the only case I can think about. Other questions? All right. So if there is no other question, I'll share the Jamboard with the TAs. And that way, if you need to go back over what we did today before tomorrow, you'll have access. Okay. And tomorrow we'll just go fast. We'll go a bit faster. It'll be really proving this thing. This result, and giving you a sense of the type of thinking, the type of tools that enter into analyzing procedures of this type. Okay. All right. Bye-bye, everyone.
Thank you.
Thank you.